Thank you for the kind introduction, and thank you to the organizers for the invitation. It's my great pleasure to be here today in this fantastic location with this fantastic and very energetic audience, talking about three of my favorite topics, Minecraft, AI, and research. So very excited about that. Before I dive into the details, I want to give you a small sense of what I usually work on. So in my day job, I lead a team of about 12 people. You can see most of my team up there in the corner. We work in Cambridge, about an hour and a half from here, in the beautiful building that you see down there. And together with my team, I share the strong belief that this is a fantastic time to do research at the intersection of AI, with a particular focus in my group on reinforcement learning and modern video games. We're mainly driven by two kind of North Star directions. In the long run, we want our research to enable new game experiences for players. So, for example, understanding what kinds of new, fun, engaging experiences the latest advances in reinforcement learning and other AI techniques could give rise to, understand what is still missing to get there, and then focus our research on tackling those key challenges. For example, understanding how in future games AI characters and humans could genuinely collaborate in order to solve hard tasks and create fun game experiences. Our second motivation is the game developer. Again, we believe that there are huge opportunities in leveraging advances in AI and reinforcement learning for game development, and our vision is that at some point we want to enable every game developer on the planet to use, for example, reinforcement learning as part of their game development pipeline. And again, that vision motivates a lot of the research challenges that we're tackling. For example, looking at how to achieve more robust, more sample-efficient reinforcement learning with predictable outcomes that game developers can control to get the behaviors and experiences they would like to enable. Moving from there are three topics that we're particularly excited about that I want to discuss with you today. The first is Project Malmo, an AI experimentation platform that my team built that enables AI experimentation to answer a wide range of questions. Secondly, I will tell you about our competitions that we're running on top of the Malmo platform, and in particular our latest competition, the mineral competition, focusing on sample-efficient learning from human priors. And third, I will give you a brief taste of some research challenges and how we're tackling those today. So let's dive into Minecraft. Just to get a show of hands, who here has played Minecraft before? That is way more than half. Fantastic. Who has played it for more than 10 hours? All right, still a lot. Okay, fantastic. So you all know what I'm talking about. And for those of you who haven't played Minecraft before, just very quickly to catch up, Minecraft is one of the most popular video games, one of the most popular modern video games. It's a sandbox game of worlds that are procedurally generated. And it's 3D worlds that characters, players go, explore, they socialize. And what's really interesting there is that Minecraft is really more of a meta game. So when human players play the game, there's not even a small number of ways in which the game could be played. It's really this meta game where people go in, they come up with their own ideas of how to play the game, and there's a huge variety of, for example, mini games or emergent plays or kind of projects that people take on and how they play the game. What that means as a platform for AI experimentation is that on top of this sandbox game, we can create tasks, worlds that are essentially infinite. You can create as many new tasks for an AI agent in there as you want, and that means that this platform, kind of building on top of the Minecraft game, you can drive research from simpler tasks to things that are more and more challenging, all the way up to tasks that involve, for example, collaboration in complex settings, including collaboration and communication with human and AI agents. So when we started to look at this game as a platform for AI experimentation, our goal was to unlock all the potential of this hugely exciting game for AI experiments. And for this reason, my team built Project Malmo. a platform for AI experimentation that was as open-ended as possible. So we support Windows, Linux, and Mac OS. We support a huge number of programming languages, many different ways of setting up and running experiments with the goal of keeping this kind of open-ended nature and enabling as many people as possible to leverage this for their research. We've been really humbled to see the uptake in the community. There are more than 100 papers that are now using this, have already been published and use this for their research, ranging from experiments in cognitive science to understanding how natural language interaction could be enabled on a platform like this. So today I want to give you just a quick overview of what kind of how to get started with the platform and how in principle it can support a wide range of AI research. I will show a few examples of how we've used this, and a lot of that is going to be in the space of reinforcement learning, but I want to emphasize that this platform is much wider than the couple of examples that I'll be able to show here. And if you're interested in discussing kind of what the capabilities are, I'd be really happy to discuss that offline. As mentioned, Project Malmo is open source. It's available on GitHub, so you can go and try out the examples that I showed today. What if you want to get started in using Project Malmo, let's say for reinforcement learning experiment? As you know from the morning, this is the typical interaction loop. So the key problem that you face when you want to start running such an experiment is that you need to get an agent. It needs to be able to send actions into the game, affect some changes in the environment, and then get back some kind of observation about how the state of the world has changed and some kind of reward signal in the case of reinforcement learning, which is then the signal that it can learn from. Now, with our platform, here's an example of how we can make this happen. So this is a really very first boilerplate example of how you would go and code up an agent that interacts with this world. So you have a little bit of boilerplate for setting this up, loading a mission, which is the task in our notation. And then you start to enter this interactive loop where, as long as that mission is running, the agent can get some information about the current state of the world, potentially a reward signal, and it can send actions to this world. In this example, we'll just hard-code it to move, turn, and jump, wait for a moment, and then continue. And so you see that kind of getting started, creating that initial interactive loop is really straightforward using the platform. And within a couple of minutes, we can have this agent jumping and turning and moving around a very simple Minecraft world. Now, the power of that is, of course, not just that I can create this example and have an agent jump around in this world. The power comes from being able to combine such a simple interface with this capability for creating virtually infinitely many different tasks. And just to illustrate what it's like to create a new task within Malmo, I want to show this example, which is a 3D rendering of a classic reinforcement learning task, cliff walking, which is here taken from the Sutton and Bartow Bible on reinforcement learning. This example is actually part of the starter kit or the tutorials, so you can try this out very easily at home. The task here, in case you're not super familiar with reinforcement learning, you have an agent navigating this world. It's initially, it doesn't know anything about the world that it's interacting with. So even though here we see renderings of lava, we can see the blue goal in the far back. The agent initially starts with a blank slate, doesn't know anything about the task at hand, and so it has to learn from trial and error how to achieve its goal. Before we go to that, we'll look at how would we set up this task. Briefly, the mission XML defines a number of handlers on the server side, so how to set up the task, as well as on the agent side. So how does the agent perceive the world, and how is the task specified? We can start this from any arbitrary Minecraft world. So that could be one that is just generated using, in this example, the flat world generator. That could be any Minecraft world that you have built, and maybe there's some kind of scaffolding or some setup for the task. So this really creates a lot of flexibility. On top of that, we can add decorators that can, for example, generate whatever elements in the world we want and that we want to have some programmatic control over. In this case, we're going to create the platform that the agent is placed on, as well as as randomly generating some gaps in that platform. Next, we need to look at the agent. In the case of reinforcement learning, that means that we need to define the observation and the action space. So how does the agent interact with the world? And there's a lot of different possibilities within Malmo, ranging from visual observations to more symbolic state observations. In this case here, we are going to use observations from full stats, meaning that we get a symbolic view of the world. And in this first example, we'll use a symbolic representation to do tabular Q-learning in this case. Along with this, in this case here, we can define what actions the agent has available for movement. In this case, it's going to be discrete movement actions. Also, in this case, we don't want the agent to destroy any blocks, so we're going to disallow the attack command, for example. Finally, very importantly for reinforcement learning examples, is that we need to define some reward structure. And again, there's a wide range of handlers available to define the reward. In the example here, we would have the agent get a big negative reward when it falls in lava and a big positive reward when it reaches the blue block at the end, as well as a small penalty for every command that it sends. And with a single page of XML in this case, we define this task for the agent and replicate in 3D in a very visual way this classic reinforcement learning task. Now, if we couple this with a reinforcement learning agent, in this case tabular Q-learning, as you know, initially the agent would learn from trial and error, initially with an exploratory policy where it takes actions at random. And here we can actually see very visually what that means. The agent randomly navigates and explores the environment, initially dying in lava a lot, getting a lot of really valuable experience for learning here. What's really nice here as a starting point is that this is a really good way to kind of understand the concepts that happen here. In the example here, if we started with someone who wants to learn more about reinforcement learning and Q-learning, for example, we can use this as a really nice teaching tool. For example, looking at how Q values are learned in reinforcement learning, we can kind of explain that Q values here are the expected state action values, so the expected value of taking an action in a given state and then following a policy from there onwards. Now, as you may know, in Q-learning, these action values are estimated from the trajectory, so from the accumulated experience, and these values are bootstrapped from the earlier estimated values. Now, here, because this is a tabular setting, we can actually really nicely visualize this, where we're showing here the Q table, all the values of all the states and actions that the agent has tried so far. We can visualize the values that are currently being estimated. And as the agent is learning, this is a really nice way to visualize and see how learning is progressing over time and get a good understanding of how Q-learning actually works. Finally, after about 10 minutes of training, we get a policy like this, where the agent has gotten a reasonably good estimate of the Q values of the entire state action space that is reachable, and it has learned to reasonably reliably navigate to the goal. So again, a really nice way to get started, for example, with reinforcement learning. But of course, as I mentioned, the platform is very open-ended, very extensible, so we can go very easily from something that is a teaching tool and kind of starts building up the basic understanding of reinforcement learning and Q-learning. We can now go one level higher. We can plug in a deep neural network to do function approximation instead of learning tabular Q values, and we can get an agent that learns from the visual input as opposed to the symbolic state. And we get an agent that, for example, here observes the 4 most recent frames, learns to interpret those appropriately, and it can navigate a maze or some other environment purely from the visual inputs. Just to give some examples of research that we have done kind of just after releasing the platform, One work was with our brilliant intern Lydia Liu, who is now at Berkeley, where we looked at the degree to which deep reinforcement learning can actually generalize across different variations of tasks. So for example, different mazes where the lava is located in different locations here. And we found that the representations that are actually learned by those are very nicely interpretable, and the agent actually learns specific clusters of areas where it faces dangers. So that was one of the kind of first works that showed that agents can learn models or representations that generalize beyond the very, very specific task that it has been trained on. A year later, at AMAS 2017, we also showed that the agent is able to learn to generalize to completely unseen combinations of maze layouts and visual configurations. In this work here, we focused on fast learning from imitation data in those environments. Again, we're able to show that the agents are able to generalize very well to those kinds of maze tasks. A third piece of work that was not directly done on Malmo, but as a kind of study within Minecraft to understand how agents and humans could interact with each other. I want to mention this study because it's quite different. It's quite a different collaboration from the ones that we usually do. This one was a collaboration with our intern Fraser, as well as then postdoc Eva, where we looked at how human players would choose to interact with a smart AI agent in Minecraft if that agent had the capability of interacting with natural language. And so this was really exciting to me because this was a study that allowed us to ask what-if questions. So before we get to the point of actually having an agent in there that intelligently interprets my natural language commands, how can we build up a study that allows us to test how people would accept this, how they would interact with this agent, how they would play with it? So the kinds of what-if questions that we wanted to ask here was, what if a teenage player of Minecraft had some sort of intelligent sidekick? What if that sidekick could understand natural human language, could be taught new things, and that the player could ask for help? What are the kinds of things that people would try out and would want to do with those agents? And what are the kinds of pitfalls, maybe for the development and design of those agents, that we should keep in mind as we push to solutions that could eventually actually enable those kinds of scenarios? So in this case, we focused on kind of how the players would interact, what kind of natural language formulations they would use, and what challenges they might encounter. As you can imagine, we faced one problem setting up this study. We're not quite at the point where we can plug in smart AI agents that communicate with players using natural human language and really understand what's going on. So we needed to find a way to study this while giving a good setup that was plausible and a plausible way of testing out that interaction. In the study here, we opted for a so-called Wizard of Oz design, where under the hood, our friendly helper helpbot here was actually controlled by a collaborator, by one of our researchers, in order to kind of create this experience of what it would be like to interact with an AI agent of the required capabilities. And of course, this was we had to make sure to follow ethical guidelines, get IRB approval for this, and we made sure to debrief people after they had participated in the experiment to make sure they understood that they did not actually interact with an AI character, and that in fact AI capabilities were not yet at the level portrayed by the system here. But so, as mentioned, this was a Wizard of Oz setting. Under the hood, helpbot was controlled by a researcher, and here we looked to create a behavioral script that we thought would be plausible for where we saw kind of the future state-of-the-art in natural language interaction approximately 3 years from that. I think we're maybe almost at the level that we characterized here in the behavioral script. I'm not sure we're all the way there, but I think a lot of the things that we were testing out are actually becoming feasible either now or will be feasible in the near future. So essentially, our behavioral script was that the AI character would be able to recognize objects in the world. It would help the player with mining, fighting, and building. Most of the settings were building tasks, so we didn't really get into testing out those other situations as much. We tried to predict players' intentions when they were simple, and that did create some ambiguity. We learned a lot about kind of how much people assume to be simple, even though that might not necessarily be the case. We wanted to kind of provide the impression of learning from simple player feedback. So if the player mentioned something or pointed something out, our bot would remember that. And the bot was able to understand simple natural language inputs. So now, very interestingly, of course, what kinds of messages did the human players choose to interact with those bots? The vast majority of commands was, as expected in the build task, commands or some kind of request for help. And this is something that we had heard from people anecdotally before, so it was interesting to see that confirmed again. A lot of Minecraft players said, well, if I want to build a big structure, the most boring part is just getting a lot of the materials. So I'd love to be able to just say, go get some coal or some oak planks in order to kind of help with building that structure. So that's something that we confirmed here that worked quite well. There were a lot more ambiguous things in there, for example, copy me. And if you think about it, that can create a lot of ambiguity for an AI character. When do you start copying? When do you stop copying? What parts, what actions are actually intended as part of the demonstration? When do you stop? So there are a lot of interesting cases to consider there. Just to point out some of the challenges, if we wanted to make this bot a reality, there's a lot of variation in language. I think within on the order of 300 messages that we encountered, there were very, very, on the order of 5% repeat messages. So we're nowhere near the kind of exhausting the variation in the language, even for simple tasks like this. And we expect that a lot of variation will be there, even as that were to be scaled up. There's a lot of ambiguity, as I already mentioned, not just in harder tasks like copy me, but even for oak planks. Is there a specific location where those should be gotten from? For example, one problem that players ran into was, well, what if I just build some structure? How does the agent know that I don't want it to get planks from the structure I just built, but rather get new trees, new materials over there? So how do you kind of provide that information? And that also moves into this area of there's a lot of implied world knowledge that people use. And so it's really interesting to think about what it would take to provide at least some level of that world knowledge, how much of that needs to be provided to get to the point where a reasonably intuitive natural language interaction is possible. A much smaller number of interactions were around feedback. One of the more common kinds of pieces of feedback was stop. We had instructed our researchers to just continue a task until something happened, and so there was this need to at some point go in and tell the help bot that, okay, it's enough, you don't need to do that anymore. Again, even among those messages, there are quite a lot of different ways in which people phrase that. Stop collecting dirt, don't mind that, you don't need to make any more planks. It's interesting both in terms of what specific action does the stop refer to, but then also looking at this from a point of view of, could this be used as some kind of feedback, for example, if the agent were to learn and improve its performance. Similarly, there's occasionally positive acknowledgement, as you can see here. Again, there's quite a lot of variation. Some of it is very context dependent, and most importantly, this is very sparse. So there were a lot more commands, a lot more interactions with the agent than we got these kinds of feedback signals. And so again, if we wanted to get agents to interact based on purely natural language, this would be a challenge to understand how this could be interpreted as a signal for continued learning. A second kind of point that was very it kind of came out very strongly in the study was that engagement between the players and the help bot varied quite dramatically. And so that ranged from some people barely interacting or not interacting at all to some seeing this as a really interesting kind of thing to try and figure out and understand better. One hypothesis that we have is that the kind of interaction that a player shows with this character is very much based on their initial expectations, combined with a very quick kind of learning loop of just testing out the capabilities of whatever it is that they're interacting with, observing the response to that, and then to some degree updating that mental model of what it is that the agent can do. We did realize that that observation or kind of updating of assumptions was very, very partial. So in many cases, players did not fully observe what the character actually did. They assumed that things would happen that didn't happen. And so as a result, there was a lot of mismatch in terms of what the model was that the player had of the character and what actually happened and what the actual capabilities of the characters would be. So again, there's some really interesting kind of lessons here in terms of how to scaffold or how to enable human players to probe and understand what a more intelligent character can actually do and help them kind of understand to what degree their assumptions may or may not correspond to what that character is able to do. The initial expectations that we mentioned are crucial. In our study, we gave the agent a very robotic form. As you probably remember, it's kind of this help bot, robot kind of surface that we showed earlier. And we think that that framed or kind of bootstrapped or scaffolded a lot of the kind of expectations that players had. A large part of the participants did consider the help bot as a toy, as something that was more robotic. And it would be really interesting to follow up and see to what degree those expectations or assumptions would hold or maybe would change if we gave the character a form that is more animal-inspired, or maybe more like a human player, or maybe something that is completely fantastical altogether, and that could really, it's really important to note that beyond the algorithms, beyond what we put under the hood, this surface makes a huge difference in terms of how people actually interact and to what degree they perceive the character as something intelligent. Right? So as I've shown, kind of Project Malmo has already enabled and continues to enable a wide range of research in AI, in reinforcement learning, and very importantly at the intersection of AI and many other disciplines. One other area that we're really excited about is the set of competitions that we have organized and that we continue to organize on top of Project Malmo, most recently with our fantastic collaborators at CMU, Preferred Networks, Queen Mary University, and other locations, and in the form of the mineral competition. To give you a brief kind of historical overview, back in 2006 was when Project Malmo first went public and people were able to start using it for their research as well as teaching and other purposes. The following year, we organized the first competition on top of Project Malmo, the Collaborative AI Challenge, where we set up a goal of getting an agent that could interact with a human player to solve a collaborative task. In this case, it's a variation of a classic game theoretic task, the stag hunt, where agents have to decide whether they want to collaborate or whether they want to defect on each other, and they, of course, can get a much higher reward if they are able to collaborate, but that requires some amount of trust. We had really interesting findings off of this competition. Here on the picture is our team together with the European winners of the challenge. The task was essentially solved this year, and classic AI techniques, for example, graphical models, really won the competition this year, that particular year. A main limitation was that the task did not require a lot of generalization. So the task was solvable using techniques, for example, that didn't do a lot of kind of complex function approximation. And so based on those really interesting insights from our first competition, we then followed up with the competition that would really focus on generalization in these hard collaboration challenges. So that was the starting point for the Marlowe competition. A lot of the people here at the conference were actually involved in setting that up. And the paper led by Diego on the multi-agent reinforcement learning Marlowe competition, which was presented at the NeurIPS 2018 competition workshop, as well as a whole workshop at AID last year, kind of summarizes the setup of the task and the challenging missions that we created to really push the community in the direction of coming up with generalizable approaches to learning to collaborate on these kind of complex social coordination games. This version of the competition is nowhere near solved. So there was a lot of good progress on this. The winners of the competition proposed an approach called Deep Mimic, where they started off of some demonstrations of the task from human players, but there is a lot of room for improvement. And we think that kind of this problem of learning reasonably data efficiently how to collaborate in these extended two-player games from kind of pixel images or from some kind of observation that allows generalization is really an unsolved challenge. And so if you're looking for a challenging project that in my estimate will take at least a couple of more years to solve, then this is a really interesting set of tasks to look at. Those are all available online, and so I would encourage you to take a look. This year, we, for the first time in our competition history, stepped away from multi-agent tasks and decided to really double down on this question of how can reinforcement learning agents learn to generalize in a complex environment with limited amounts of resources. And so that, under the leadership of a fantastic team of CMU, led to the NeurIPS 2019 competition that's called the Mineral Challenge. So I want to spend a few more slides just giving you a sense of what this challenge is about and why it's so exciting. As with many of these kind of large efforts, it takes a village to get this to happen. So here you see our fantastic organizing committee as well as external advisors. As mentioned, this is something that's running in connection with NeurIPS right now, and you can see the NeurIPS competition paper already out on arXiv, which is a great resource to learn more about this challenge. Briefly, what is this about? The starting point is the Minecraft tech tree. So if you haven't seen this, this is a limited subset of all the items, all the materials, all the technologies that can be found or developed within the game Minecraft. And you can see the huge amount of complexity here. So some people, I mentioned people play this in many different ways. There's one way of playing Minecraft where you discover this entire tech tree. So you start from zero, you go through, you have to develop all the materials yourself. And so it takes days and days and days for human players to go and get to a reasonable level of technological development in that setting. In the competition, we're not trying to solve all of this at once, but we picked out one task that we think has a right balance between kind of something that is far enough out so that it requires innovation, but it's also something that we think can be solved within a reasonable kind of amount of time. So the challenge goal is to develop an agent that can learn to obtain a diamond with limited compute and data. And so I want to emphasize here, because I think one of the key innovations of this competition is to propose a very systematic way of limiting the amount of samples, the amount of compute that the agent can actually use during training. And we believe that this is really important in order to push reinforcement learning in the direction of sample efficiency, of making use of potential additional data sources, and we'll see that we have a large amount of human demonstrations available in this case. So we think that those kinds of data sources can really help, but we think that new innovations, new algorithms are required in order to push RL to be much more sample efficient. In this case here, competitors submit a Docker container with all their code. The agent is evaluated by first retraining it from scratch. There is an amount of 4 days available for training, and then after that, the agent is evaluated. So this means that any of the participants' agents here will be trained on at most 4 days on a very specific set of hardware on a single machine. I think it's a really exciting setup to try and push the community in this direction. Some really interesting questions here. We think there's a lot of structure that can be used in order to address this task. For example, the obtained diamond task, when started from scratch, requires the agent to use navigation, for example, to get to a tree. It needs to chop down a tree, start to make pickaxe and additional tools. Finally, it needs to find a cave, dig down into the rock, avoid dying in lava, find some diamond ore, and mine that. So it's quite an interesting sequence of steps. To make things a little easier and hopefully feasible, we are providing one of the largest human demonstration sets available so far, 60 million state action pairs, and we believe that there's huge potential for new innovative approaches for using this kind of data in order to arrive at an algorithm that is able to learn in a sample efficient way. Now, quick video to give you a slightly better idea of what the task involves. Awesome. I hope that got you all really excited about participating in the competition. Just to give you a sense of where we are, the competition has started. The submission website is open, but there is still plenty of time to come up with a smart idea and submit your agent. Because the agent is retrained from scratch and has to be trained on that limited sample of 8 million frames, you will not have to train your agent for weeks and weeks or months on months. You know that you can start a week ahead of time and still come up with a smart idea. It's now a month out, so the first round will end September 22nd. So if this is an area you're excited about and interested in, maybe come talk to us over at the booth after the talk or later in the day and learn some more about this challenge. A few more things I want to emphasize. The organizing committee is very much committed to creating a competition that is as open as possible to the widest possible community in order to make, for example, travel to the nearest workshop more feasible, more affordable to a wider set of people. There is an inclusion at NERIP's travel grant. The application deadline is October 1st. So if you want to participate and potentially attending the workshop at NERIP's would be challenging for you, then by all means, I want to encourage you to take a look. Also tell everyone you think might be interested in this. A quick reminder, the competition website is online, as you see over here. You can learn about the competition. You can actually go and play Minecraft on the server in order to contribute more demonstration data for future iterations of this competition. And of course, you can participate, come up with your own agent, and submit it to the competition. We have a set of baselines that are provided by our partner Preferred Networks. These are also available online on GitHub. They're a fantastic starting point to kind of kick things off and get an initial agent. Very excitingly, new imitation learning baselines are coming out soon, so keep an eye on this. And finally, as I mentioned, the inclusion for travel grants, inclusion at NERIP's travel grant application is open right now. with that, I want to check how much time I have. 4 or 5 minutes? Okay, so I'll do a very, very quick pass on some of the more further out research challenges and some of the things that we're currently excited about. There are 2 pieces of work that I want to focus on, and those are both in collaboration with 2 awesome PhD students that I have the pleasure of co-supervising as part of the Microsoft PhD Scholarship Program. The first one is by my PhD student Steindor, who is at Imperial, co-supervised by Mark Dyson-Roth. The second one is Louisa Sindgraf at Oxford, co-supervised by Shimon. The area that we're exploring together is the area of meta-learning. And the motivation here is that learning multiple tasks is easy for people, and the more experience we have with specific variations of a task, the easier that gets. For example, once you know how to drive your first car, learning to drive the second car becomes easier, and then the third car and the fourth car. And it's actually quite similar to gaming. Once you know how to play a game of a certain genre, the next time a game like this comes along, you'll be able to pick that up initially in hours, maybe eventually in minutes. So this is the kind of thing we're trying to enable. Just here for comparison for cars, the initial estimate is that for a completely new driver, learning to drive a car takes about 45 hours of lessons plus 22 hours of practicing. As people get more experienced, a new car can be driven in the order of a few days down to a couple of minutes. So just to get you a sense of how we're thinking about this, I want to talk about the formulation of meta-learning that we're using here. I'm going to skip those details and just give you a short intuition on this. So typically when we talk about reinforcement learning, the very standard formulation is that of a Markov decision process that looks something like this. You have some initial state, S0 of the world that your agent observes. The agent takes some action A0 in that state, gets some reward signal, and the world transitions to the next state S1. So this abstraction is really important. It tells us that the next state observation only depends on the previous state and the previous action. And we can make use of that by learning policies that don't depend on the entire history of the interactions between the agent and the environment. And in fact, we can, for example, just learn the transition function for a specific task, as well as the reward function and a policy. Now, in order to make effective use of multitask information, we need to augment this in some way. We need to assume some structure that gives rise to a multitask problem that we can then exploit in our approach. And so for the setting here, we assumed the simplest possible thing, namely that there is one additional variable, in this case m, that modulates both the reward function and the transition function of the underlying entity that the agent is interacting with. And so in this 2 works, we looked at how this simple model, how this kind of initial model can give rise to very quick multitask learning. Just to give you a quick sense of the results here, this was work where we focused on modeling this using latent variable Gaussian processes, where the tasks are assumed to be embedded in some low-dimensional space. So you can assume, for example, or you can imagine this, for example, in the car setting. You can imagine that there are a small number of parameters that tell you how a car reacts. For example, how quickly does it accelerate, how responsive is the steering, how responsive is the brake. And as you're usually not told what those parameters are when you get into a new car, but with a few minutes of experimentation, hitting the brake once, hitting the accelerator, you'll be able to get a good sense of how the car reacts, and you'll be able to very quickly adapt to this new task. That is something that was really challenging for single task agents, but with the setup that we propose here, we can show that, for example, in this initial toy experiment, our setup is able to very, very quickly adapt to new tasks. In this setting, it's supposed to just learn the setup of a function. It has to learn and model the dynamics and the underlying functions purely from training data that it gets about initial tasks. And then with one additional data point at test time, it is able to correctly estimate the task that it's supposed to solve. This one we evaluated on a multitask hard-pulled setting, and we're showing here that, in fact, the low-dimensional representation that the system has learned very well corresponds to the layout of mass and length that we would expect if the agent had access to those underlying parameters. So we had a really good proof of concept here. And we've seen that this kind of model, shown here in blue, is able to learn a wider set of tasks much more quickly than previous approaches. Just to give you a quick sense here, this was work led by Luisa and published at ICML this year. This one looks at essentially the same underlying model, but looks at starting this from a much more flexible approach that uses deep neural networks in order to do the function approximation and learn the structure of the task. In this case, we start from a fast adaptation approach called MAML, and we show that, in fact, this can be augmented to only learn the context parameter of the specific task in order to very, very quickly adapt to a new task at runtime. Now, I'm going to skip the details here for time reason, but encourage you, of course, to take a look at the paper. I just want to give you a kind of quick sense of what this looks like in a domain that's very common for reinforcement learning experiments here in the Mojoku domain. So we see here a half cheetah that is supposed to learn different tasks. In this example here, there will only be two tasks: move forward or move backward. And then at test time, we'll want this agent to adapt as quickly as possible to the direction that it's supposed to run in. So this is a pre-trained half cheetah, and we can see initially when we run it before kind of meta training, the agent just hops around in place. It doesn't quite know which direction it's supposed to go. After a single update, in this case, it's already able to figure out that it's supposed to move backwards. So with just a single rollout and a single kind of backward pass, it's able to pick up on the task and moves backward. And as we do 2 and then 3 gradient updates, the agent is able to move backwards much more efficiently. These are all quite early demonstrations of those types of approaches, but we believe that this kind of setup of meta-learning and the ability for agents to very, very quickly learn new tasks has huge potential. For example, in settings where, let's say in a game, an agent is required to very quickly learn a new task or to quickly adapt to new opponents. So we're really excited to see how far this can be taken and where this can lead to in the future. So just to wrap things up, we started with the Malmo platform, and I believe that this platform raises a huge number of challenges that are really exciting, both in terms of what kinds of applications they can lead to, for example, for gamers and for game developers. At the same time, they provide really hard challenges that are worth tackling from the AI and reinforcement learning side, as well as in collaborative interdisciplinary research. So just to give a few examples, pushing towards more sample-efficient learning approaches could give rise to much more robust tools that learn from limited data. We're really excited about this area of adapting to new tasks very quickly. And an area that's very close to my heart and that the team is focusing on is to understand how agents could learn to communicate and collaborate both with each other and with human players. This brings me to almost the end of my talk. I just want to give a quick call out to the various ways in which my colleagues at Microsoft are involved here at the CoG conference, starting tomorrow with Anthony, who's going to give a demo of a game that is supposed to teach reinforcement learning concepts to especially game developers. Then also on Wednesday, our former intern Dino is going to present joint work. And Sam is going to participate in the panel of AI in games competitions. So if you want to learn more about game competitions and Sam's view on those, I very much encourage you to join. Finally, for Wednesday, Adam from the MSR Montreal team is going to announce the winners of the text word competition. So again, something I'm hugely excited about. Continuing on Friday, there's then work that is led by Daniel Hernandez, and where Sam is a collaborator that looks at a generalized framework for self-play training. And last but by no means least, work led by our current AI resident, Luke, on Maze Navigator, a customizable 3D benchmark for assessing generalization. So again, very much in the spirit of encouraging more robust, more sample efficient, and more generalizable reinforcement learning approaches. With this, I want to thank you for your attention. Thank you.